Welcome back to Integral Calculus. In this video, I want to talk about separable differential equations. The category of separable equations is probably my favorite type of differential equation to solve because it takes a little bit of thought, but not much mechanically. Once you see the solution, actually solving it is generally fairly straightforward. Let me get my head out of the way and let's dive in. I'm not going to give you a definition of a separable differential equation. A separable differential equation is an equation that can be solved using this process. How about y prime equals t times y? What I notice right away looking at this differential equation is that it's harder than the ones we've dealt with before. It has y prime and y in it. The other thing that I notice right away is that there's no addition or subtraction. When there is addition or subtraction, it can be harder to separate the variables in the differential equation, but when everything is multiplication and division, then it's not going to be too bad. I'm going to rearrange this equation by dividing both sides of the equation by y. That might seem a little bit strange, but that gives us why we have the name that we have. On the left-hand side of the equation, I have y's. And there's only one term on the left-hand side of the equation. It has y prime, it has y in it. On the right-hand side of the equation, I only have t's. It can be more complicated on the right-hand side. I can have anything that's going on there as long as it's just t's, and in theory, I can integrate it. But that's exactly the key. In theory, I can integrate it. And in this particular case, integrating it is not that bad. On the left-hand side, I have the integral of y prime over y dx. I'm sorry, not dx, dt. I'm in a calculus mindset and not a differential equations mindset, so I keep wanting to use x. All right, so y prime over y dt is equal to the integral of t dt. And that left-hand side looks really complicated, except that that's actually just a u substitution away from a very simple integral. I'm not even going to bother calling it a u substitution because I really want to substitute in let u equal y of t. So I'm just going to write down that as a reminder. Well, dy would be y prime times dt. And oh, that's right there. And that is the entire key to separable differential equations. You want to have on the left-hand side y prime dt multiplied by some function of y. If you can get that, then you are golden. So I can now substitute in and rewrite this as dy over y. And that's really great, because now I have a very straightforward equation to solve. The integral of dy over y is the natural log of the absolute value of y. The integral of t dt is 1/2 t squared, and my original two functions were equal to each other, but when I integrated, they could be different by at most an arbitrary constant. So I have a plus c hanging out in here. All right, let's see if I can do a little bit more. Well, I have natural log of y. I'm trying to solve for y. So I guess I can use the exponential as the inverse of the logarithm. That'll give me that the absolute value of y is equal to e raised to the 1/2 t squared plus c power. And then if the absolute value of y is equal to this, and remember, e is a positive number raised to any power always comes out as a positive number. So y itself is plus or minus e raised to the 1/2 t squared plus c power. Technically speaking, with that we are done. But in practice, you'll almost always see a couple of additional steps taken. Because I've got all this stuff in the exponent, including some addition, we're generally going to split this up and separately look at e to the c times e to the 1/2 t squared. Right? The product rule of exponents says when you're multiplying like bases, you add the exponents. So I haven't changed anything, but I have given us a very interesting target right here. Because remember that c is an arbitrary constant. If I raise e to an arbitrary power, I can get any positive number I want out of that. And then I can choose plus or minus, so I can get any positive or negative number that I want. So no matter what number I want, I can choose a value of c so that plus or minus e to the c gives me that number. Plus or minus e to the c is an arbitrary constant. And so we can condense it, we can simplify it, and just call that whole thing one arbitrary constant. Generally, we use the letter a, just to make it something different from c, but you can use any value or any letter you'd like there. It's just a new way of writing the arbitrary constant. It's still an arbitrary constant, though. Generally speaking, when you're reading through an example in a textbook, or especially if you're talking to somebody who studies differential equations, most of the process we went through here is going to be done in the blink of an eye. If I was trying to solve this equation professionally, remember it was y prime equals ty. I'd probably write out y prime over y equals t. I'd then write out the integral of dy over y equals the integral of t dt. I would write out that the natural log of the absolute value of y is equal to 1/2 t squared plus c, and then I would write that y is equal to a times e to the 1/2 t squared. Those are the steps that you would see in a textbook. Every textbook assumes that all of the stuff in the middle is completely obvious and no one would ever struggle with it. I don't have a clue why they think that, but that's what they think for some reason. I don't want you to be able to do that. I want you to be able to work through this logic step by step. So if your work looks more like this, I'm going to be happy. If you can convince yourself to make your work look more like this, then I'm not going to complain because that's what my work looks like. But yeah, that's something to strive for after you have taken a course in differential equations and possibly even a second course in differential equations. The textbook authors who think that you should be writing like this are absolutely crazy. All right. How about y prime equals t squared over 2y? I think it's even more obvious in this example that this is a separable differential equation. If I multiply both sides of the equation by 2y, I get 2y y prime equals t squared. Then from here, I can integrate. The integral of 2y y prime dt is equal to the integral of t squared dt. On the left-hand side, I'm going to use that, I guess, u substitution, but y prime dt is just dy, so we have the integral of 2y dy equals the integral of t squared dt. You will get so used to that you forget to write the intermediate step out, but I don't expect you to be there yet. Right, directly integrating from here, the integral of 2y is just y squared. The integral of t squared is 1/3 t cubed, and then I'm going to have my plus c. Then, to get y by itself, I'm going to take the square root. If y squared is equal to this, then y itself is plus or minus the square root of 1/3 t cubed plus c. And unfortunately, there's nothing else I can do to simplify further. That just is the solution here. I want to go through one more example before I wrap up on this, because I've given you some examples where it's relatively obvious that the answer is that the equation is separable. It doesn't have to be. If I have t times y prime equals 3y plus 2. This does not look separable at first glance because there's addition. But if I divide both sides of the equation by t, I'll get y prime equals 3y plus 2 all over t. And now, I'm going to divide by the entire numerator, 3y plus 2. Y prime over 3y plus 2 equals 1 over t. And as ugly as it was, I just successfully separated my variables. I have y's on the left-hand side. I have y prime multiplied by everything on the left-hand side. I have t's all on the right-hand side. Those are the things that I needed in order to say that I've successfully separated. Now, I can integrate. The integral of y prime dt over 3y plus 2 is equal to the integral of dt over t. Right. This time I really do need a u substitution. So whether or not you replace that, I'm going to let u equal 3y plus 2, and then du is going to be 3y prime dt. So I need an extra 3 up here, which means I need an extra 1/3 out here. And then I can write this as 1/3. The integral of du over u is equal to the integral of dt over t. Those are both natural log integrals. So 1/3 natural log of the absolute value of u equals the natural log of the absolute value of t. I've got some work to do from here. Couple of different ways you can approach this. How about let's start by multiplying by 3. So the natural log of the absolute value of u is equal to 3 times the natural log of the absolute value of t, and then bring that coefficient inside, which gives me that the natural log of the absolute value of u is equal to the natural log of the absolute value of t raised to the third power. Let's go ahead and take the exponential from here. Almost had enough space to keep everything on the screen that I need. But I'm going to get that u, or I guess it would be the absolute value of u equals the absolute value of t cubed. Natural log is 1 to 1, so the natural log of two things are only equal if those things are equal. Absolute value equation, u must be equal to plus or minus way back here, I forgot to write my plus c. That's going to be important. Because it's actually not a plus c. Like, wait a second, something's going on weird here. All right, let's try that step again. Natural log of absolute value of u is equal to natural log of the absolute value of t cubed plus c. Well, e to the natural log is going to cancel each other out. I'm going to get the absolute value of u. And then I'm going to have e to the natural log of the absolute value of t cubed plus c. And from there, I'm going to use the same trick I did in that earlier example. I'm going to write this as e to the c times e to the natural log of the absolute value of t cubed. And then e and natural log are going to cancel each other out. So I get that the absolute value of u is equal to e to the c times the absolute value of t cubed. There we go. Now I'm back on track. And then again here, same trick. If I have absolute values, then the arguments inside could be plus or minus. So u is equal to plus or minus e to the c times t cubed, and plus or minus e to the c is some arbitrary constant a. At this point, finally, I'm going to go back and remind myself that u is equal to 3y plus 2. And solve for y. So definitely crunchier than the other examples, but still something that we can get through. And that's what's important. The other thing that's important here is recognizing how much exponentials and logarithms show up when you're looking at differential equations. That's actually not a coincidence, and that's the reason that I put differential equations and exponential functions in the same unit. Because we use exponential functions as the solutions of differential equations, that's actually the entire reason that exponential functions are useful. You think that exponential functions are useful because of exponential growth and decay models. As we'll discuss in the next video, exponential growth and decay models are just differential equations that somebody's already solved for you. But before we get there, I want you to get a little bit more practice looking at separable differential equations. So I would like you to take a look at y prime over t is equal to y over t squared minus 1. Hopefully a little bit more approachable than the last one, but definitely going to be crunchy. Take a couple of minutes, see what you can do playing around with that one, and I'll see you in the next video.